All right. Okay. All right. Okay. All right, guys. So, how do I get to the line of best fit in the R? Where do I go? Stat. Calc. Yeah, the one that's got a line in it. And then you do it. If you remember, we used that before. I'm going to pretend like I forgot how to do it. All right. And again, by God, anytime something is freaky with your calculator, you just come up and ask me. You don't put a note on your final and say, oh, man, I would have done this. I would have kicked its ass if only. Just come up and freaking show. All right, so we got R of 0.919, which is definitely evidence of what?
Strong correlation.
It shows strong correlation. Okay. So it's definitely evidence. What about if it was 0.54?
It's decent but weak.
Yeah, it's weak correlation. What if it was 0.51? No.
There's no.
No evidence of correlation then.
No.
It wouldn't. I couldn't even use the line at all then. So R's got to be bigger than this to show evidence that there's any kind of correlation at all. And then the closer it is to 1 in this case, because it's positive, the stronger that correlation gets. The tighter the points get to the line. You guys with me? So below this is no evidence of correlation. I couldn't use the line at all. 0.54, I would still use the line, but I know going in it's probably going to suck. Right? But this is 0.919. That line's going to be pretty damn good. And what line did we get? We got 1.03x plus 61.87. Oh my God. Okay, so where do I go to get the line in? Y equals, that's crazy. That was our old line from the other time. Get out of there. 1.03x plus 61.87. Now, the graph right now, it's going to be bullshit. Aw. Yeah. Anytime I put new data in, I hit zoom. And for most of you, it should be 9. And there you go. That's what everybody was showing me. That picture, basically. You guys with me? So you would bring this up to me at the desk. You would show it to me. I would initial. I love it when somebody brings me a calculator and it's correlation for a different test version. And I'm like, no, get away from me. They just borrowed somebody. Let me show them this. No. So be very careful. There will be several different versions of the test that will make cheating so obvious. So you come up and show me, yeah. Interpret R. That's its own question. And Joe is ahead of the game here. What'd you say, Joe?
Strong correlation.
Strong correlation, sure. Or you can say decently strong, whatever you like. All right, I like it. And what does it tell us about the line of best fit? That's a separate question. We trust it. Anybody said something different?
It's tied to the data.
Good. Tied to the data. I like it. Anything like that. We can trust it to make predictions, so forth. So there are 2 questions here. Don't just tell me this and stop. I need something more specifically. I like it. if somebody did 13, I could do it directly by just plugging 13 in, because X represents number of homeworks. This is true data, by the way. And then I can calculate this, or some of you guys are asking me, how did you do this? If you hit second calc value, you could just put a value in for X. So I get 75.26. I like it. Some of you guys got close to that. You might have rounded more or less than I did. Coolness. Everybody okay so far? Okay. There's a website called Spurious Correlations that do things like the suicide rate in Michigan versus the price of butter, and there's a correlation. So there are correlations in the wild that just happen randomly. So of course, we don't decrease the price of butter and fewer people kill themselves in Michigan. That doesn't make any sense. But there will always be a correlation somewhere that just kind of exists. You always have to follow it up with more deeper analysis. This is a very surface level analysis. Was this really difficult? No. So more than likely that means it's not enough to really get in there and see what's going on. This is pretty straightforward. You do more homework, you probably should do better. I mean, that's kind of makes sense. Hopefully. Okay. What the hell's R equal negative 1 mean? What? So that's why I say it like that, because I know that's probably in some of you guys, that's why I use interesting words like hell and shit, damn. Not the F word too much. Gotta be careful what you use, fuck. R equals negative 1. Well, why was this so good? Close to 1, right? The closer to 1 it is, the stronger it gets. So 1 must be the strongest. It must be perfect. It must mean it's so tight they're actually all on the frickin' line. Negative would just mean they're all on a negatively sloped line. It's a good idea to draw the line first and then put dots on it. We're just making some shit up here. If you put the dots down, then almost never line up nice. Anyway, you guys with me? You want to see something really funny? You're all like, I don't know if your definition of funny is the same as mine. Remember those problems in algebra when they would say, find the equation of the line through 1, 4, and negative 2, 18. Remember those? Yeah. Watch. Just go with me for a second. If you would have known back then. 1, negative 2, right? Those are my two x values. So here's 1.14, negative 2, 18. Can anyone tell me what r is going to be? Any 2 points has how many lines going through them? 1. Any 2 points defines a line. So r is going to either be 1 or negative 1. It's going to be perfect correlation. It's only 2 freaking points, right? So watch this. It's kind of neat. If I do this, it actually tells me what the algebra teacher wanted from you. It tells me the slope and the y-intercept. And look, r is negative 1. Why is it negative? Because when x goes down, y went up. Anyway, sorry. You guys sort of get that? Do you remember that problem? I'm sure you do. Yeah. Find the equation of the line that goes through 3, 5, and 4, 8. Yeah, do y minus y1. Remember that? We did that. We actually did that in here. Well, the calculator will actually find the equation of the line through any 2 points perfectly. Too bad for you. Haha. Sorry, I get too big of a kick out of that. Everybody cool with that problem? So that's why the closer we get to 1 or negative 1, the better, because they are the perfect situation. The minute I take the points away a bit, r starts to go down, away from negative 1 or 1, negative 0.99, negative 0.9. You guys with me? I can just imagine pulling the data points apart and watching r change. Okay, now here is the way that I like to word a problem on a test. Something like a final that you might have. You have to understand that this is a uniform distribution. That's what you expect to happen. And like I kept telling a few of you guys, would you expect there to be more 1s or more 2s or more 3s? No, there's no reason to expect it. Now, at the same time, I totally understand. If you roll the die 120 times and you got exactly 21s and 22s and 23s, that would be freaky. Right? Do you guys agree? If you flip a coin 1,000 times, you got exactly 500 heads. That would be a little freaky, right? So even though that's the most likely thing to happen, it's still actually a small probability. It's the largest probability, but it's still a very small probability. So it's much more likely that something else would happen, something close would happen. Yes. So if I roll a die 120 times, and there are 6 sides to that die, how often should each die show up? On average, 20 times. 120 divided by 6. Right? So if it's uniform, you just divide the total by the number of categories. They each get the same amount. Right? If I had $120 and there are 6 of us, and I have to divide it evenly, how much will we all get? $20. Right? Can't trust me though. I probably have $200 and I told you it was 120. Second thing is, so this expected should be 20s. Observed is exactly what it says. It's what we saw. What did we actually see? 17 ones. This is not expected. This is what we saw. 18 twos, 19 threes, 16, 22, 28. Now this isn't that hard to do in your head. The difference is 3 squared is 9. The difference is 2 squared is 4. 1, 16, 4, 64. But again, you could do L1, L2, L1 minus L2 squared. Right? You could do all that in the lists if you wanted to. And then I divide each of these by the expected. So I basically multiply by 5 and move the decimal over twice. But oh, shit.
3.2.
Thank you. I didn't feel like doing that. And I think they add up to 4.9?
4.9.
Somebody got 5.1. That's pretty close. That should be a 1.6. What happened to you? Good. All right. And what the hell is this? Now, see, this is what I used to call chi-square star. It's just too busy. This is my chi-square that I calculated. It's just like z star. What do I have to compare that against? The critical chi-square. How far away did I have to get? I know how far away I got. What would 0 mean if I got a chi-square of 0? What's the only way to get 0 out of this? Is if all the expected and the observed are the same. Because what do? I take the difference between them. The only way I'm going to get 0 is if they're the same. And that would mean that looks like really good evidence that it actually followed what I expected because it exactly did. And again, why can't I just stop here and go, well, that ain't the same as that shit. It's evidence that it's different. I mean, if you roll a die 120 times, like we said, do you really, really, really expect this? Not really. You expect close to it. So is this close enough to this?
Yeah.
That's the question. Just like hypothesis test. So what's your critical chi-square? Now, what's the degrees of freedom? 6 categories minus 1 is 5. I like it. And then my alpha is 0.05. So I go to 5, 0.05, 11.071. So I'd have to get to 11.071, and we got to 4.9. So did we find evidence that they are not the same? No, we didn't find evidence that we can't say that this is a good die. I just didn't find evidence that it isn't. I know it sounds like semantics, but if somebody is found innocent, does that mean they didn't do it? No. No, of course not. Holy shit. We got a lot of examples, and I'll let you guys come up with them. Right? You guys with me? So that's why the reject and the support, which I'm not going to make you right here, but back to hypothesis testing, that's why the wording was important. You wouldn't say, we found him innocent, he didn't do it. No, you found him innocent. We don't know if he did it or not. I mean, that's, right? There wasn't enough evidence to say that this person did whatever. That's all that means. Doesn't mean we accept that they're innocent. It means we failed to reject that they're innocent. See the difference? That's why the words are important. Maybe? All right. You're all like, there's too many words in this math course, but too bad. Okay. Any questions on this stuff here? So I here's what's going to happen. Let me talk about. Let me grab that in a second. I want to talk a little bit about section 11. What was it? 6. Yes. Stay. All right. Do you remember how I was trying to remind you guys that the normal curve exists on its own? It's got its own formula, that freaky-ass formula we looked at once. It's in the book. But how do we use it? We have all these different z-score formulas that follow that form, right? So what goes with this form? This goes with that form. This goes with that form. This goes with that form. Oh, God. Oh, Bartlett. All right. Each of these look very different. I try to describe to you how they're really sort of the same idea, but they are different formulas that all refer back to the same shape. Are you guys? They all follow the same shape. So we have a shape now, right, which I affectionately refer to as Java. But, all right, we have the shape skewed. Right? I love it. So that's the chi-square distribution. We know that this follows that form. Here's the other one. Here's the one that I started off talking about this, was standard deviations. What is the... So if I had a population of ages, what's the smallest standard deviation I could get from a sample from those ages? So if I took a sample of 3 people, what's the smallest standard deviation I can get from those 3 people?
It's pretty big.
No?
It's pretty big, but
What do you mean pretty big? No.
it's a small sample.
So if I took a sample of 3, you guys, what's the smallest standard deviation I can get? And of course, what does standard deviation measure? How far away the data points are from the mean. Well, what if all 3 ages are the same? What's your standard deviation then? All right, 0. There you go. What? I love you, Joe. Order up. It's not a question about correlation. We're not doing a correlation study. It's just calculating standard deviation, right? So if I have a set of data and all the data are the same number, the standard deviation is 0. Are you guys with me? That corresponds to this being 0. Remember this, the sucky thing about this is it's not symmetric. It doesn't have equal negative and positives like the z-scores do. This starts at 0, and that's another reason why it starts at 0, is because the smallest standard deviation I could have is 0. So here's this. Do you see how these relate what we see to what we expect, or what the average is, right? What we see to what we expect. I like it. So if I took if I knew the standard deviation of all ages in here was 6, what would you expect the sample standard deviation to be? Freaking 6. I like it. You expect this population, that's your best guess. So here is the standard deviation version of this. Let me see which way I want to write it. I think the book does all this. So look what this does. If I take a sample and I get a 0 standard deviation, that would be here. And there shouldn't be that many that have a 0. I shouldn't, like if I have a whole population of ages and I take a sample of 50, there shouldn't be a lot of ways to get 50 people with the same age. And the same thing, if I get way up here, that means that this is way bigger than this. And that shouldn't happen too often. So what should happen most often is they should be close to each other. And that's that big chunk in the middle. Now, why is this distributed like this? Because I can get huge standard deviations. Huge. So I can take a sample, I can have a normal population of ages, and I could take a sample, I can get an 87-year-old, a 98-year-old, and a 3-month-old, and an 8-month-old. This standard deviation is going to be freaking huge. You with me? A little bit? Not really, no? Shit. Not at all. Damn it. So the same thing with this. If I have a mean, and I take, let's say I have a normal distribution of ages, and I take one person, I would expect their age to be close to this, wouldn't I? That's why this middle part is so big. Because I expect most of them to be close, right? Not very many should be out here. Well, standard deviations do the same kind of thing. If I take a sample, I expect that S to be close to sigma. Should be in the middle here. There shouldn't be a lot of zeros. There shouldn't be a lot of 300s. There should be most of them close to this. So that divided by that would be 1. So the peak actually happens at n minus 1. Maybe. So this is just another chi-square formula besides it. The same way that this and this and this are all z-score formulas. They all refer to the same picture. So both of these refer to the same picture. So I can use the chi-square chart for both of these situations, right? So, I didn't want to say this first. I will say this now. I'm not going to make 11.6 do. I'm going to make it extra credit. If I would have said that first, you guys would have definitely tuned out. You know, like, damn you, Jeff. I was taking notes and shit. It's 11.6 extra credit. What it does, you ready?
Yeah.
Now let's see, anybody interested in doing this, listen. So remember how with a normal distribution, to make a confidence interval, I would do this and I'd find whatever this was, this would be the positive part of that, right? Well, that shit ain't gonna happen here. So if I wanna make a confidence interval, I'm gonna have a chi-square small and a chi-square big. That kind of explains why the chart has that two kind of sections to it. Now watch this, watch. If you're tuning out, please just shut up. Thank you. Watch how I can solve this for sigma. I just have to do this really.
Yeah.
Stay with me now, right? Ooh. Now, if I put that in there and that, if I put that in there, I get the lower estimate for what this is going to be. So what I'm doing is, what did we do to make a confidence interval for a mean? We found x bar, and then we went up and down from it and said we are so confident this interval can be. So here, I get an S. And I do put this in there to get a lower range of the interval, and I put this in there to get the upper range. Right? Actually, I got it backwards, but so it's going to look like this. My confidence interval. So I would think that the variance would show up in between this and this. Now, why is this one the upper? Because if I divide by a smaller number, my result is bigger. Yes? So this would be, I would say, I'm such and so confident that this interval from this to this captures the true variance. And what do I do if I want standard deviation? I just take a square root. So if I take a sample and I get S, is that the real standard deviation of the population? No. This gives me a way to construct a confidence interval, the same way we did with means. I just can't use this freaking distribution, for standard deviations because the shape is governed by the standard deviation. So I needed a new shape. I needed a new distribution that they would follow, and it's this one. All right. That's enough. And so if you want to do 11.6, that's on you. You can do it for extra credit. I'm not going to make it do.
Why is it to the left, the sky?
Again, if you divide by a bigger number, the result will be smaller. So that's the lower edge. Yeah. Okay. So what do I want to do with the rest of my time is I actually want to try to give you guys a chance. There's a ton of shit this semester. I wanted to devote part of this class to start kind of like a review for the final. And then the next class is going to be entirely devoted to review for the final. I will have an answer key for this next time, but we can certainly look at this.
The other one?
The practice final, yeah. So if you want to do another goodness of fit test, we could. If you want to do a hypothesis test, we could. Whatever you want to focus on. Some of you guys are like, I want to focus on going back into my bed. I understand. I just want to focus on chapter 1 through 12, Jeff. Focus.
Focus on chapter 12.
Yeah, we can focus on chapter
1
12.
through.
Or if you just want to pick a problem off the practice final, start trying it out. Whichever problem you have the worst time with, that's cool too.
The checklist thing, like how we had the definitions.
Yes.
Are
Yeah.
we going to be?
Those
is this
definitions
part of
will.
the review or is this part of this?
Yeah, the practice final is nuts and bolts. Here's the problems and the concept, whatever I said that was,
This is
the checklist.
definition.
It's just if you look at the checklist and you're like, I have no idea what that means. Maybe go back to the chapter and refresh your memory. Now, I was ultra geek. I would study so well that if you said an idea, I could tell you which chapter and which section it was in. Right? Oh, no. Don't do that to yourself. I did too, man. What are you talking about? And I was working 3 jobs, and I was walking uphill both ways. Didn't have shoes. Could afford shoes. There you go. There you go. It was snowing, even though it was July. It was crazy. Our house didn't have a floor. Yeah. Oh, that's the Z-score question? No, what exactly would a... Yeah. All right, guys. So you always want to know exactly what's going to be on the test. And a long time ago, I told you that question would be on every test, including the final. Unfortunately, I've come to the realization that I'll probably never get 70% get that right. You always tell me something about area with that problem. I didn't tell you it was normal. Plus, even if I told you that was normal, if I said, what does a z-score of 2.8 tell you for normal distribution? You still couldn't give me area, because where did you get the area from? The chart. That's what the chart tells you. What does a z-score by itself tell you? Yeah, how many standard deviations? So if I say, what's a z-score of 3.13, just to make something up, you would say that data point is 3.13 standard deviations away from the mean. Even better would be above the mean, that's why it's positive. But if you just say away, I'm cool with that. That is fundamentally what a z-score tells you. Huh? Every test. And I tell you what, I don't think I hit 50% getting that right yet.
Yeah.
But it's that many standard.
Yep. Away, or if I said negative 1.98 z-score, then the best answer would be that data point is 1.98, standard deviations below the mean. Now, if you just said away from the mean, I'm not going to take points off. But if you put below, I get a little tear. Like, oh, that's awesome. That's all the negative means. It's below the mean.
Oh, so which line would you use?
Maybe it's the wrong.
But I mean, if you're using this line, then you could use those points. Who is this? You know, otherwise you can use a point like there. So you go to the point.
Because remember when we studied that all night, it would go to like a 90% surface.
Oh, I just looked at all the, yeah, I looked at all the data. Because that's the data. No, that's the data, yeah. That's an area. So if you look that up, yep, that's an area. We don't know this until we're trying to find it. Oh, just like I was saying, we need to merge this with this. It tells us that it's 0.27. Do the homework for 11.6? Yeah. So